Good morning, everyone. So the thrust area, the fifth thrust area, is called Discernment Verification, and effectively it's a set of different projects that are working on doing technological development necessary for enabling new type of treaties that not only go after the delivery vehicles in arms reduction treaties, but also after the specifically number of the warheads. So to step back a little bit, to understand what the problem is, let's consider the New START Treaty, which is the most recent treaty signed between United States and Russia, which stipulated a number of the deployed warheads will be reduced down to about 1,550 each. Okay. However, there's a lot more warheads around. There's like large stockpiles, and there's also a number of warheads that are not even stockpiled, that let's say are being retired. So that actually the total number of warheads, instead of being say 3,000 deployed, are more than 10,000. Okay. So question is, where does this come from, and why, and how do the treaty partners actually verify each other's compliance when it comes to the number of the warheads? So they don't really check each other's compliance with warheads. They specifically focus on the delivery systems. Okay. Delivery systems means ICBMs, it means cruise missiles, it means strategic bomber aircraft. And the reason they do that is because it's easier to verify. So here's an example of a KGB operative who is checking this Gremlin cruise missile as part of the 1988 INF, Intermediate Nuclear Forces Treaty. So they're checking to verify that this is an actual cruise missile before it's sent for dismantlement and disposition. This is an example of Americans checking the SS-18 Soviet-made ICBM, again verifying that it's real before being sent for dismantlement. And a somewhat more recent example is as part of the START-1 treaty, the Americans agreed to chop down 365 B-52 strategic bombers, which were significant force, strike capability. And what people did was they took them to the desert in Arizona. They used guillotines to literally chop them up and left there in the desert. And Russian satellites came overhead, took pictures, verified that in fact 365 bombers were destroyed. So when it comes to delivery systems, it's fairly easy to do visual qualitative checks and verify that these are real systems before being sent for dismantlement and counted towards the partners' obligations under the treaty. And this leaves behind the problem that you have this very large non-deployed surplus warheads that are not accounted for in the sense of the treaty itself. Okay, so that leaves open the chance for theft, which can lead to nuclear terrorism, a proliferation risk, and also there's always a chance that there's a risk of rapid rearmament in case of a political crisis or things like that. So the question is, can we come up with technologies that will allow us to verify, authenticate warheads, which will in their turn enable more ambitious, more aggressive treaties that will specifically go after the warheads and not just the delivery systems? Okay, so what's the general idea behind this thrust area? So treaty verification, first of all, is not the same thing as weapon detection. Okay. Literally, treaty verification is really about verifying that an object X is in fact an object X. Okay, so you have some treaty accountable item verifying that it is what the prover is claiming it is. So in order to do that, we have to negotiate, we have to develop and then negotiate protocols which will establish acceptable levels of what we call confirmation, okay, without leaking any information. So when it comes to a verification protocol, the few parameters that are the critical parameters are ability to clear all warheads. Okay, so this is the completeness. Okay. If you will, this is the false positive probability. You want to keep it very low. The next one is being able to detect all the fakes or the hoaxes. Okay, this is also referred to as soundness, or you can think of it as a detection probability of a hoax. And finally, the third one that we're not so used to think about is the requirement not to reveal any classified information. Okay. So this is, sometimes people refer to as zero knowledge, that I put it in quotes, only because in information theory, zero knowledge is an extremely hard requirement, where literally there's no information coming out. Really what is relevant over here is that no useful information comes out. Okay. So for example, if they find out that there is less than 30 kilograms of plutonium inside the bomb, that's a useless information, because of course there's going to be less than 30 kilograms of plutonium. So now, what are the thrust subgroups or sub-projects that are working here? There is a group at the University of Michigan that's working on inherently trustworthy instruments For verification, it's led by David Weehee. Claire Solomon at UIC is leading an effort on information barriers with enhanced automated isotope identification. There's a collaboration between Princeton and Yale that are developing a zero-knowledge template verification protocol. And here at MIT, we're working on a physical cryptographic verification of nuclear warheads, a different way of trying to solve the same problem. And I also list the number of national laboratories that people are collaborating with. So let's go one by one. So verification using inherently trustworthy instruments. Something I did not talk about at all is that there has been significant effort in this area, primarily through information barriers. Okay. So one of the limitation of information barriers is that there's a few, but one of them is that you are relying on electronics to achieve the information barrier itself. Okay. So there's a few problems with this. One of them is that in principle, someone could circumvent this. Someone could launch side attacks against various components of the electronics and try to extract some information that otherwise should not have been revealed. So question is, and really what it comes down to is information barrier systems are made of thousands of components. So really validating and verifying that they do what they say they do is itself a very difficult task. So the question is, instead of having to rely on this whole maze of electronics, is it possible to come up with individual components that will play this critical role and they will be much easier to verify, much easier to trust? Okay. So the approach, so for example, what you would like to do is you'd like to be able to acquire spectra from, for example, for some radioactive object like a plutonium pit or something like that. And you just want to be able to see the few peaks that would allow you to validate this object. But you don't want to see this continuum that can hide lots of classified information. So ideally, you want to have, for example, some kind of an ADC chip, an analog to digital converter, that will have very high resolution where you need it and zero resolution where you don't want to see anything. And you'd like this to happen at a fairly simple scale so that it's easier to validate. So one approach to perhaps do this is using flash ADCs. Flash ADCs eventually have like a series of comparators. You could cut out a bunch of these comparators and leave only the ones that correspond to the range that you want. The trouble with the flash ADCs is that they're quite limited in resolution, that mostly can have 8-bit flash ADCs, and you really need something like 12-bit. So the project that Dave Weehee's group is working on uses successive approximation ADCs. Actually, most ADCs we use in our electronics are successive approximation, which allow much higher bit depth, down to 12, 14, 16, etc. But they modify this concept quite a bit. So instead of having a regular SAR ADC, they use a SAR ADC that has specific ranges, okay, very coarse ranges. So that that coarse ADC, if you will, outputs some kind of a simple level output, which then gets sent to a differential amplifier that calculates the difference between the coarse output and the actual analog signal. And that difference is then being amplified by a regular ADC. The two signals eventually get combined, and you end up having something which has a high resolution of the second chip where you need it, and no resolution outside of that range. And the important thing over here is that if you try to launch side attacks against this chip, you really learn nothing. So one way to launch a side attack, I can skip that, you can look at the power consumption of the chip itself. And from power consumption, you can figure out what it's doing. However, if you have a very coarse ADC, like I described, the power consumption reveals absolutely nothing about what number is being conferred. So the group has already built a prototype chip, that fits on a 2 by 2 millimeter piece of wafer, and additional research is being done in this direction. The second thrust area, the second subgroup in the thrust area is the information barrier project in Urbana. Okay, so this project primarily focuses on ways to effectively decompose spectra. For example, here's a sodium iodide spectrum from a burp bowl that was taken in the DAF. Okay, and try to infer information about various peaks that are hidden inside this spectrum. So most spectra that you observe are extremely convoluted, right? It's a convolution of a bunch of peaks that are continua all added together. So is there good ways to do this inference? The technique that they are pursuing uses wavelet transforms. So wavelet transforms, in terms of intuitively thinking about it, essentially you can think of it as an extension of Fourier decomposition. So we can think of Fourier decomposition as like a special case of wavelet transform, with the difference is that in Fourier decomposition you have the components themselves, which are sinusoidals, they're defined in a frequency space, but they're not defined in time domain. The wavelets are defined both in the frequency space and they are also defined in the time space. So it's more like a wave packet. Okay. These wavelets create an orthonormal basis, which allows you to do these decompositions. So some of the examples of their results is they have done identification of a few of the peaks from plutonium and americium, and they have achieved more than 80% detection ability from the burp ball using a sodium iodide detector. So the burp ball was also covered by 4 centimeters of polyethylene. To go a bit more into these details of what the technique is, essentially you can think of the decomposition in the form of this spectrogram, where this is the x-axis is the energy, and the y-axis is the scale. And the scale, you can think of it as effectively an analog of frequency or the resolution. Okay. So as you are changing the frequency and the resolution of the possible signal, okay, for every possible value, you end up getting some maxima that result in this kind of traces for different values. And since for your detector, you know what its acceptance function is, you ought to know what is its intrinsic resolution. So this black line corresponds to the values that you would get for specific value of energy. So the intersection of this and the intersection of these traces give you the particular peaks that the spectrum is essentially made of. Okay. So here you are in the spectrum where you have quite a bit noisy spectrum, you are actually able to infer, for example, that I believe this is the I think it's 2.4 MeV line over here. Here are some of the examples for a variety of sources for which the data was acquired, also at DAF, and the identification that they have been able to achieve. Every once in a while, there's also false alarms. So, for example, iodine 125 and europium 152. Right, and there'll be another talk later on by Claire Sullivan, which will go more into these details. Right. So the Princeton and Yale group are working on zero-knowledge template verification. Just to kind of give a quick background as to what it consists of. The idea that they're pursuing essentially is that you have two weapons that you are trying to compare to each other. The notion is that you have a golden copy, and that's your template. You are trying to do a zero-knowledge comparison to a candidate warhead. Okay. This is a general scheme that also we use at MIT. And the notion is that the hosts get to produce a preload, which you can think of as a negative of the transmission image of the weapon itself. So they make a negative, and then after that you expose it to the positive, if you will, and you ought to get in that case a completely flat image with just Poisson statistical noise on that. Okay. So Poisson noise, flat image, zero knowledge. Okay. On the other hand, if someone tries to change the candidate weapon somewhat, since the inspectors get to pick which preload goes to which weapon, there's at least 50% chance that they will catch such a diversion. Okay. And if you want to have the probability higher, you can repeat this process a few more times, and the probability of a successful cheat will go down as 1 over square root of 2 to the end. So here's a set of measurements. They published the concept a few years ago, and they did experimental measurements where they built this little alien with long rabbit ears. And so this is like for the honest case, you have the actual positive and you have the complement, which is effectively the negative, if you will. And once you do the actual exposure, you end up getting something completely flat. However, if you have a hoax where the ear is missing, you add the complement, and now you are getting this non-statistically significant deviation from Poisson noise. Okay? And this will be essentially your ability to reject, to catch the hoax. So a set of measurements have been done over last year using a 14 MeV DT source, the PPPL, using a variety of different metal cubes to essentially create this phantom, if you will. And additionally to that, there have been a number of measurements that were performed at DAF using active interrogation on HEU. Now, the question is, what detector do you use to create these negatives and positives? Okay. Most detectors that we're used to work with, work in time domain. So effectively, they produce like a volatile information. You either capture the signal when it comes out, or you lose it. Okay. The fundamental difference of the detector that they're using, these are bubble detectors. So these are superheated gel droplets in an emulsion. okay, which, assuming they're not exposed to any radiation, can stay in the superheated state for a long time. However, if the droplets get hit by a neutron or by any particle that causes ionization with a large d over dx, you will have cavitation. Okay, so you'll form a bubble. So effectively, this is a counter of actual neutron hits. But in addition to just simply being counter of all neutrons of all energies, by changing the temperature and the pressure, you can set a threshold at which this cavitation will occur. So by changing the temperature and pressure, you can select where your energy cutoff is. Okay. So in that regard, it's very useful. But also, because it's effectively you have these bubbles, you are not in time domain, but you are in coordinate space. And that allows you to effectively create these preloads where the host can go and individually create the bubbles by irradiating for as long as they want. And then these bubbles will stay there. Okay. So in that regard, these detectors work very differently from most detectors that we work with. So the group at Yale is doing the research for this detector development. They're primarily focusing on really getting the threshold as precise as possible at 3 and 10 MeV. Okay. In addition to just making bubble detectors that you can count by eyeball, where you can just go and count the individual bubbles, they're also looking at ways to use light scattering from the bubbles themselves as a way of automatically counting the bubbles. And in addition to that, they're looking at ways of taking pictures of the bubble detector and using image analysis software to determine the number of the bubbles, to automate the process. All right. I'll simply mention that the Prism Group is also working on information-bearer experimental systems, as well as open source software which would allow different parties, hopefully future parties of this treaties, to verify and hopefully confirm that the software in information-bearer system is what it is, that is reliable. I will, in the last few minutes that I have, I will very quickly talk about the MIT part, and then our student, Jason Vavrek, will go in more detail. So in our case, at the MIT case, we try to achieve the same goal as the one that Prism is following, but we do things quite a bit differently. So our goal is also to do template verification, compare golden copies to candidate warheads. But what we do is we're using Bremsstrahlung beams. So we illuminate a weapon, say, let's start off with a golden copy, Bremsstrahlung beam. And after the beam has gone through the weapon, we end up getting this NRF filtered Bremsstrahlung spectrum. However, so this spectrum over here has classified information about the weapon, but we don't measure that. There's tons of shielding between the detector and this thing over here. So what we do is that then we put a foil of an unknown composition, and we end up getting a signal from the foil, which is the convolution between the isotopic makeup of the weapon and the foil itself. Okay. The comparison I always do is think of checksums. If you have got a file, you apply a checksum, you get a hash. If you have two files, you run checksum. If the hashes match, it means the files are the same. And then the important thing is that from the hash, you can never reconstruct what the file is. So that allows you effectively this physical cryptography that will enable to do comparison and still not find out anything useful. So then we switch from a candidate, from a template to a candidate, and that allows us to do the comparison. Just very briefly, we have done simulations. Last year focused on primarily doing simulations. We showed that if we compare a template to a hoax, we end up getting very large discrepancies, making our technique very sensitive to small isotopic modifications in the object. This has been published. That said, I'm going to skip to the last slide because I'm out of time. So the accomplishments and the work in progress that's taking place in this trust area. There has been an experimental proof of concept demonstration that was developed at Princeton. The Yale group is continuing their optimization of the bubble detectors. At MIT, we are working on the NRF concept. And there has been, the Illinois group is working on data that they have acquired from the DAF facility. And the University of Michigan is developing these methods for advanced, if you will, information barriers inside small electronic devices. With that, I'm ready for your questions.
The physical cryptographic measurement using NRF. So to start, we have a parallel beam, the Bremsstrahlung beam incident on a rectangular warhead. So that's an approximation there.